transformers for high resolution image synthesis, also known as VQ-GAN. So we're going to go over an introduction, architecture, and the loss functions, the conditional synthesis, and then experiments and conclusion. So just to start us off, basically the authors kind of gain inspiration from the sort of two stages approach. The first stage is they using a VAE, an encoder and decoder. An encoding of the data is first learned. Something like this: you have your encoder on the left and your decoder on the right, and then that learns the sort of latent space, and then a probabilistic distribution is then learned on that encoding latent space. So there's that distribution there. So one of these architectures that implements this is VQ-VIE. So VQ-GAN is built on top of VQ-VAE. So it's important to kind of understand how VQ-VAE actually works. So what it does is it learns a discrete representation of the images, and that's the novel thing about that. However, this only works on low resolution data, so it doesn't scale well to high resolution image synthesis. And then the global interactions aren't captured well because it uses convolutional density estimation, which only works on, well, local space typically. So then the authors, there's the encoder on the left, the decoder on the right, and then
can you use a cursor? Show us where you are. Tell
yes.
us, yeah.
And then, oh, there's not a cursor, but then in the red box here, this is where the authors start changing up the VQ-VA network. But Mehdi's going to talk about that a little bit later, so I'm not going to go over that just yet. So the author's hypothesis is that low-level image structure is well described by a local connectivity, whereas higher semantic levels are not locally connected. So just take an example of like a image of a squirrel per se. So up close you have the fur, which is a kind of very patterned texture, and it's dictated typically by local space. Whereas if you zoom out of that picture, those local connections are less meaningful, and you have to start looking at it from like an overall global high level perspective, and that's their hypothesis. So the idea is to utilize transformers for high resolution image synthesis, take convolutional and transformers together, and use a convolutional approach to learn a codebook, which we'll talk about later, and then learn the global compositions of these images, and then use an adversarial approach to ensure the codebook learns the most important parts of the images. And with that, I'm going to pass it off to Mehdi, who will talk about the architecture of VQ-GAN.
Okay, can you see my screen?
Still, are you sharing the screen? Because he hasn't the D. Yeah, now we can see.
Okay. So for understanding this architecture, we need to have a certain background. So first of all is the adversarial training procedure which GANs are taking advantage of for generating word-like images, and I'm sure all of us are familiar with this concept. The autoregressive models, which are I'm going to explain it in a fair bit, and the quantization, which is the codebook. Autoregressive models are the notation is actually AR of P, which P is the order of the autoregressive model, which means the autoregressive model is going to predict this index, the index T, from how many previous indices. For example, the Markov processes are actually one of the autoregressive models with the order 1. Because they only are dependent on the previous step. So this is a simple autoregressive model, which actually says that the T step is going to be predicted or computed from the P previous steps. So for the code book, it's actually the trainable matrix bag of visual words. So as you see here, in this image, we have, for example, this image consists of these visual words. This image consists of these visual words, and this image consists of these visual words. And if we want to represent this image with all these visual words, we can do that. So basically, the code book is a trainable matrix of visual words which are trainable. So as for the architecture, the presented architecture in the paper is something like this, and I will break this architecture down for better understanding. First, I'm going to talk about the CNN encoder, and then I'm going to talk about the quantization and the code book, and then I'm going to talk about the CNN decoder, the adversarial training procedure, and at the end, I'm going to talk about the transformer, autoregressive transformer. So the encoder part takes the image X through a CNN encoder, and they name it E of X as a function like, and this produce a feature map, Z hat. And the encoder architecture that they used consists of these layers, which given an image from a dimensionality of H and W, which is the height and width and the channels of the image, it will transform it to it will give us the small HW and NZ, which NZ is the dimension of each token in the code book. So these are the actual layers that they use in this.
So do you know, Mehdi? Do you know what's the NZ? What's the number NZ? How many?
The NZ is actually they use different numbers in this paper. So they used 32 and 16 for the NZ.
Okay, thank you.
Yeah. So for the quantization part, they use this equation for the quantization part. And if we look closely, this is just nearest neighborhood algorithm. So this, if we have this code book Z and we have this latent space features, which they named it Z hat, if we extract this block, which is the block Z hat 1, 2, we actually going to take the Euclidean distance between this each part of the each token of the code book with this block. And if we do that for the index 0, we get for example 12. For 1 we get 100. For 2 we get 8, and for I we get 4. So the minimum argument in this Euclidean distance are argument ith. So we replace this block of the feature map with the ith block, with the ith token of the code book. So we get something like this. So if we do exactly this procedure for all these blocks in this feature book, we get the feature map, which is we get a feature map which is a ZQ that all the blocks are consistent of the code book. So decoder part gets the quantized version of the feature map and feed it to the CNN decoder, which they name it G of X, standing for the generator, and they get the reconstruction of that image, which they named it X hat. So the decoder consists of these layers, which are pretty similar to the ResNet. And we see that from the latent space, we are reconstructing the image to the exact same dimensionality that it was before, which is HW and C, which is channels. So that the training the code book for the training the code book encoder and decoder, they get the image which is X to feed it to the CNN encoder. They get the feature map. They quantize the feature map, which is they get ZQ from quantizing it, and they feed it to the CNN decoder, which is G of X, and they reconstruct the image. So as you see, the quantization function is not differentiable. So what they need to do is to estimate the gradients, which is simply they copy the gradient from the CNN decoder to the CNN encoder. So the loss function for this module that I just show is the something like this. So first term is the reconstruction loss, which cannot train the encoder because there is no connection between the gradients from the decoder and the encoder. The second term is the Euclidean distance of a stop gradient function of encoder output and ZQ. So a stop gradient function is actually fixes all the encoder part and just pretend that is a constant number. So there is no computational graph necessary to compute this part of the loss function. So this part of the loss function actually trains the code book for us. And this part of the loss function that they called it commitment function is a Euclidean distance between the stop gradient of ZQ. They actually freezes the code book and they train the encoder with it. So this part actually trains the encoder. Up to this point, it was just the VQVAE paper, and there was nothing more. So from this part on, it will start the novelty of this VQ-GAN paper. So for training a richer code book, they actually introduced the third network named discriminator in to train adversary and get a best code book if possible. So they feed it, they did the same procedure, and they added a third network, which is the CNN discriminator. The CNN discriminator actually gets the reconstructed image and the real image input to it, and it actually gets give us the exact dimensionality of the feature space that we had. So in this, as you see, this discriminator is different from the GANs because it doesn't just tell us that this image is real or fake. It just it says that each patch of this feature vector, the feature map is real or fake. So the whole network is trying to fool the discriminator for the discriminator to say these patches are real from the reconstructed picture, and the discriminator tries to say that the reconstructed picture from the feature maps are all fake. So this actually tries to trains this loss function trains the discriminator and the whole network. So the other part that they added to this architecture is the latent transformers. So the transformers are very good at finding the long-range dependencies. So they use the transformers as autoregressive models. So they quantize, they get the quantized encoding of X by the quantization of the encoding of X, ZQ, and they get, which is the equivalent to feature map indices. So what this transformers tries to do is generate the sequence when some indices of sequence are given. That exactly is what autoregressive do. And the image generation can be formulated as an autoregressive predicting the next index of the sequence. So for the training this transformer, they used just the ZQ and the transformer, and Kasun will go through it in details. But this transformer is directly trained from the ZQ, nothing more. And this architecture of this transformer is actually from the transformer architecture of GPT-2, which is the unsupervised language model in the natural language processing realm developed by OpenAI. So because they are going to generate high resolution data, they need bigger and bigger feature maps. So as you know, the transformers are very computationally expensive. So they introduced the sliding window transformers in order to enable them to make the feature maps larger and larger to get a high resolution data. So they use sliding window transformers, which is we saw multiple times in this course. To summarize the architecture, they used the flow of data is like this. They initialize the codebook randomly, and they feed the image through this architecture and quantize it and get image reconstruction. They feed it to the discriminator as well as the original image, and they train the whole architecture. And after training the codebook should be expressive of the features in that particular data set. For example, if the data set is images of faces, the codebook should be representative, for example, of a feature of an eye or a lips or a nose. And after that, the transformer will be trained on the ZQ in each step to perform as autoregressive. So the transformer gives us a probability distribution for each one of these indices, given all the indices that are before it. So for the data synthesis unconditionally, what we are going to do is to train, we get the trained codebook Z, and we get the trained transformer, and we sample from the distribution of the given, for example, with given SI, we have SI. So we have data distribution for it because it's a trained transformer. If we don't have any sequence before that, it just these lower I is just empty. So the transformer will give us a distribution for each part of these steps, and we sample this sample from this distribution, and we get the ZQ from the trained codebook and the sequence of the which transformers with the sampling gives us, and this will feed it to the CNN decoder, and this will give us a new images. And I will let Kasun goes on. Kasun.
Okay, I'm going to talk about loss function. So this is the architecture that Mehdi explained. So we see that, this thing has three parts. So this is the wiki VAE architecture, and we have GANs and we have a transformer. So each one associated with some loss. So we see, we say this part is wiki loss, and the discriminator loss is like a GAN loss, and then we have a transformer loss associated with it. So the main loss function is mainly consists of VQ loss and GAN loss. So like now I go back to the idea again, like, this is the image I got from the original VQVAE paper. So first, like, they represent the loss equation as the initial, like, this is the more general case. And when we know that, when we substitute e to the power of x hat square or something, this will become Euclidean norm. That means, like, the second equation is a case of the first general equation, and then the loss function has mainly three parts: the first term, second term, and the third term. So mainly the first part is optimized by the encoder and decoder, and then the second one optimized the code book, and the third one again encoder, as Mehdi said. So I'm planning to go detail into this. So so here, we see that, the vectors coming from the encoder, so these are replaced by codebook vectors. So that means, like, here we have a discrete jump, something like this, right? So if there is a jump like this, we cannot differentiate it. So that means, like, we are having trouble finding the gradient vectors. So that means, like, we cannot back propagate the gradient. So that is why we are copying the gradients here. So one can ask why we are copying the gradients, because the reason is, like, these dimensionalities are same, right? So if we copy the gradients, still we can extract some information. So, and we see that, the gradients are copying from the red line shows that, we see that no gradient is going to the top, right? So then, so we look at the loss function, and we see that, this thing has three parts. So first part is the reconstruction loss. In the paper, this is replaced by perceptual loss. And then we have stop gradient, the second term and the third term. So let me briefly mention what is this stop gradient means. Like, that means, like, we take this encoder vector, right? Stop gradient, we freeze it. Then we take the code book vectors, we try to converge these code book vectors towards it. So that means we are moving the code book vectors. So that means we are optimizing the code book vectors.
Can you show the cursor where you are? Because I'm confused. I don't understand. Yeah.
Here, right? So we get this vector, and then, we freeze it. Then we are converged towards it. So that's what this second term is doing. So this is like optimizing this part, the code book. And the third one, we do the same thing, right? We freeze these vectors, and then, we converge the encoder vectors towards it. So then we are optimizing the encoder this way. So, but, like, there is another role of the third term. Apart from the optimizing the encoder, right? That is because, like, here we are training the code book and then the encoder both, right? Because these training rates can be different. So if the training rates can be different, it can cause some other problems. So basically, so this last term, which is called commitment loss, make sure that these two are committed, right? So that is another role that these are playing. So this beta is considered as commitment cost, right? So beta is depending on 0.1 to 2 usually. Paper use it as 0.25, but it can be different. I believe our paper also use beta equals 0.25. So this is the story of the three loss terms. So I'm just basically saying again, like, stop gradients means, like, we freeze it, this vector, and then, we converge these vectors towards it. So we are moving the code book vectors, right? We are moving the code book vectors in a way this is optimized, right? So that means we are training, some sort of training it. So we do the same thing for the other part, right? So this is the general idea. And then, I said, we are going to replace perceptual loss with we replace the reconstruction loss with the perceptual loss. So idea of the perceptual loss is they found out that instead of taking the pixel wise L2 error, if they extract the error between features using the L2 error as well, then we can get a better outcome. So that's what perceptual error do, is like they get the feature maps and they extract the error between features, and then they combine it. So then GAN loss mainly consists of two parts, like, the discriminator and generator. So everyone knows about it. What discriminator do is, like, they try to
So you guys have only 5 more minutes left. I think it's too
okay.
long. Yeah.
I'll skip this part,
Mhm.
right? So then the final loss is, like, combination of VQ loss and GAN loss, and then we have this lambda parameter. Basically what this do is, like, if one of the loss is really low comparing to the other one, they try to balance it. So then, we have the autoregressive transformer. Mehdi explain it. So basically, autoregressive transformer do is, like, they send a token inside, and then, that token, a random token predict the first one, and then they send it again, and then, predict the next one. So then 1 and 42 going inside. So then, it predict the third one. So likewise, like, if we predict all the sequence, so we have to predict the next index, right? So we are sending 1, 42, 3, 3, 94, 60, 22 again to the transformer in order to predict this. So we get some probability distribution. So among the distribution, we have to pick the highest index, right? So this one has the highest, right? So let's say this is the 94th vector of the code book. So we replace here with the 94th vector. So, so like this is the equation. So this means, like, these probabilities are multiplied. In order to multiply, in order to optimize PS, we have to optimize all of these individual probabilities as well, because if any of this goes to closer to 0, then, our probability PS drops. So so basically this means, like, when the probability of S is going to 1, that means log 1 becomes 0, right? So that means loss is low. So when the probability of PS, let's say it's something closer to 0.5, then, log 0.5 is a negative, large negative number. So negative it become positive. So that means loss is really high. So that's the idea of this thing. And the next is belong to the Sanjay.
Am I audible?
Yes, you
Yes.
are.
Okay. So I'll be talking about the conditional synthesis. Just as you know, when it comes to GAN image generation, getting a control over the image generation is very important aspect, and that's where we have a provision for providing condition to the architecture in terms of VQ GAN. So let me just walk through the probabilities equation over here. So this is basically this is going to give us a probability of the next token being generated provided the condition. So condition can be anything in the form of class label or the spatial data. The spatial data can be like a depth image, low resolution image. So this is the specialty of this paper, that is not just the class label, it can also accept the spatial data as the condition. This part of the conditional synthesis has been referenced from another research paper called image to image translation using conditional adversarial networks, wherein they use architecture called as CAP6412 to generate the images. Moving ahead in the slides, I'll be talking about, sorry. I'll be talking about the image synthesis process. So I'll be considering 3 important aspects from the unconditional GAN. The first one is the codebook of unconditional GAN, which we call it as ZQ, and S is the index representation of condition C that we are providing to the network, which is derived from the codebook ZQ. We'll be calling the condition that is being provided to the network as C. And once we have all 3 in place, we're going to train a new VQ GAN on the conditional data that we have. I'll be showing up what exactly the conditional data is in the next few slides. So once we provide the conditional data as input to the network, we'll be getting codebook ZC and as well as the index representation of C from the codebook ZC trained as R. So once we have these 2 representations, the R as well as the index S that was obtained from the codebook ZQ, we're going to prepend the R with the S index representation and feed it to the transformer. Just as Mehdi mentioned in the previous slides, this is going to be auto-regressively processed in the transformer, and we are going to get a sequence generation. That is fed to the newly trained conditional decoder, and we are going to get the image generated. So this is all about the conditional image synthesis process. Next few slides, I'll be showing up few of the examples of the conditional input that we can provide to the network. First one being the cropped image, and this is what the condition looks like in terms of the cropped image. And these are a few of the synthesis variants that were obtained from the architecture. Similarly, we also have a depth image, and this is what we get in terms of the depth image. And few more examples would look like a semantically guided condition. When we provide a semantically guided condition like this, we get synthesized variants in this form. And finally, the last example would be a post-estimated condition. And yeah, this is what we get as output. Finally, I'd like to also talk about application of VQGAN, wherein people have harnessed the power of both CLIP and VQGAN to generate an image, something like this, wherein the task is to input the text input and we get the image generated in this form. So there they are using the power of both CLIP and VQGAN, wherein CLIP is basically doing the task of trying to find the best fit between the text and the input provided, and VQGAN is generating the high resolution image. So that's all about the conditional synthesis. I'll hand over it to Momal for the experiments part.
Okay. So to quickly go over the experiments and results, we need some way to evaluate the quality of generated image. We need to tell the bad generated images apart from the good generated images. So we need a clear score because there is no clear objective when it comes to generative model. So we need a score which can tell that the quality of generated image is good, it correlates with human understanding. The paper uses two scores, FID and IS. I'm going to quickly go over both of them. First score is FID score, which actually computes the similarity between features of the original image and the generated image. So if the generated images are of good quality like this, it will correspond to
There's a lot
lower
of
FID
background
scores.
noise. Mumble, you should have, done this quiet place. I mean, we cannot hear, and you guys are already, late. So already 37. Okay, just quickly summarize. Yeah.
Okay, and the second score, and if the generated images are of bad quality, so the FID score tends to be low. So low FID scores corresponds to better image quality. About the inception score, this is another way of evaluating the generated image quality, and this actually relates to the quality of the image generated corresponding to a particular class and the diversity of the generated classes. So in first experiment, they can compare their model with a convolutional autoregressive model, which is piecemeal. And here in the table, we can see that they were able to generate good lower like negative log likelihood scores as compared to a convolutional pixel snake network in constrained training setups. In second setup, they evaluated using a transformer whether they're able to go above image resolution of 256 by 256 or not, and they did went up to a 1024 by 576. So in conditional setting, they tried 4 different settings like depth map, low resolution, segmentation map, and edge image, and they were able to generate high resolution images for all settings. For unconditional settings, they introduced a reduction factor, which is nothing but how much information is encoded into a codebook. So when they encoded more information, they were able to get more coherent and real lookalike images, whereas for small f values, the images were not of good quality. Finally, they compared their model over ImageNet with some available state-of-the-art generative networks. So we can see in terms of FID score, their model is doing pretty good and doing better than these state-of-the-art networks. And same is the case in terms of inception score too. And finally, they compared their method with some existing generative model variants, and their model was not giving state-of-the-art on the ADE 20K dataset, but it gave good results on Coco Stuff dataset. And here we can also see that it's not state-of-the-art, but it's better than all of these networks on these datasets as well. So to conclude our presentation, we presented VQ-GAN, which combines the strengths of convolutional networks with transformer, that is the local correlations with long-range dependencies for image synthesis. They utilize the idea of code books or quantized vectors instead of pixels, which allowed them to harness the long-range dependency quality and avoid the quadratic computational complexity of transformers. They propose that hybrid approach for image synthesis a lot better than just state-of-the-art convolutional approaches. One bottleneck that we found in the approach was that if you want to generate conditional images using a VQ-GAN, you have to train an additional instance of VQ-GAN, which seemed like a bottleneck. And yeah, that's it.